If you're fascinated by the mysteries of time, then you need to watch this. Welcome to Brainstream X. Today, we're diving into the fascinating world of time travel and exploring the latest scientific discoveries that bring us closer to making it a reality. For centuries, the human mind has been captivated by the idea of traveling through time. Imagine witnessing historical events firsthand or getting a glimpse of the future. What was once relegated to the realms of science fiction is now a subject of serious scientific inquiry. We'll delve into the mind-bending world of Einstein's theories, where time is not absolute but relative, warped by gravity and velocity. We'll grapple with the enigmatic concept of wormholes, those theoretical tunnels that could connect distant points in space-time. And we'll explore the strange realm of quantum mechanics, where particles can exist in multiple states, potentially opening doors to time travel on a microscopic scale. Fasten your seatbelts because we're about to embark on a thrilling journey through the cosmos, exploring the very fabric of reality itself. Get ready to expand your horizons and challenge your understanding of time as we know it. Albert Einstein, the rock star of physics, revolutionized our understanding of time with his theory of relativity. Before Einstein, we thought of time as this rigid, unchanging backdrop against which the universe unfolded. But Einstein showed us that time is not absolute, it's relative. Imagine two identical clocks, one here on Earth and the other on a spaceship zooming through space at incredible speeds. According to Einstein, time actually slows down for the clock on the spaceship relative to the one on Earth. This phenomenon, known as time dilation, has been experimentally verified countless times. One of the most mind-blowing implications of time dilation is that if you could travel at speeds approaching the speed of light, time would slow down significantly for you compared to someone standing still on Earth. So, you could take a round trip to a distant star and return to Earth to find that far more time had passed here than you had experienced on your journey. You would have essentially traveled into the future. But hold on, it gets even weirder. Einstein also showed that gravity affects time. The stronger the gravitational field, the slower time runs. This means that time runs slightly slower at sea level than it does on top of Mount Everest. Now, imagine the immense gravitational pull of a black hole, an object so dense that nothing, not even light, can escape its grasp. Near a black hole, time dilation would be extreme. If you were to observe a clock falling into a black hole, you would see it tick slower and slower until it appeared to stop altogether at the event horizon, the point of no return. Einstein's theories provide the foundation for our understanding of time travel, but they also present significant challenges. For example, achieving the speeds required for significant time dilation would require an astronomical amount of energy, and the extreme conditions near black holes make them rather inhospitable destinations for aspiring time travelers. Let's talk about wormholes, those tantalizing cosmic shortcuts that could potentially allow us to travel vast distances across the universe, or even through time itself. Imagine a piece of paper representing the fabric of space-time. Now fold the paper in half so that two distant points touch. A wormhole would be like a tunnel connecting those 2 points, allowing you to bypass the vast expanse of space-time between them. Theoretically, a wormhole could connect not only distant points in space but also different points in time. Think of it like a cosmic subway system with stations at different points in history. You could hop on a wormhole train and disembark in the distant past or the far future, but before you pack your bags for a Jurassic safari or a glimpse of the world 1,000 years from now, there are a few caveats. Wormholes are notoriously unstable. According to Einstein's equations, they would collapse faster than the blink of an eye unless they were propped open by something called exotic matter. Exotic matter, as the name suggests, is pretty exotic stuff. It has negative mass, which means it would repel gravity rather than attract it. While we've never actually observed exotic matter, some physicists believe it could exist in quantum foam, the seething sea of virtual particles that pop in and out of existence at the quantum level. So, while wormholes remain highly speculative, they offer a tantalizing glimpse into the possibility of traversing the vast expanse of space-time, perhaps even venturing into the uncharted territories of time itself. Chapter 3. Quantum Quagmire, Time Travel at the Smallest Scales. Now let's dive into the bizarre world of quantum mechanics, where the rules of classical physics break down and things get really weird. At the subatomic level, particles like electrons and photons don't behave like tiny billiard balls, they exhibit wave-particle duality. meaning they can act like both particles and waves. One of the most mind-boggling aspects of quantum mechanics is entanglement, where two particles become linked, even if they're separated by vast distances. Imagine two coins flipped simultaneously, one landing on heads and the other on tails. With entangled particles, it's as if the two coins are connected. If you observe one coin and see heads, you instantly know the other coin landed on tails, no matter how far apart they are. Entanglement has profound implications for our understanding of time. If we could somehow manipulate entangled particles, we might be able to send information instantaneously across vast distances, effectively communicating with the past or the future. Another intriguing concept from the quantum realm is the closed time-like curve, or CTC. Imagine a particle traveling through space-time on a loop, eventually returning to its starting point in both space and time. While CTCs are theoretically possible within the framework of Einstein's equations, they lead to all sorts of paradoxes, like the classic grandfather paradox, where you go back in time and accidentally prevent your own birth. Despite the paradoxes, the strange world of quantum mechanics offers tantalizing hints that time travel might be possible, at least on the subatomic level. Chapter 4. Paradoxes and Possibilities. Unraveling the Mysteries of Time. Time travel isn't all wormholes and quantum leaps. It's fraught with paradoxes that challenge our very understanding of cause and effect. The most famous of these is the grandfather paradox, which goes something like this. Imagine you build a time machine, travel back in time, and accidentally kill your grandfather before your parent is even born. Now, if your grandfather died before your parent was born, then you wouldn't exist to build the time machine in the first place. But if you don't exist, then you couldn't have gone back in time to kill your grandfather. It's a mind-bending paradox that has puzzled physicists and philosophers for decades. One proposed solution to the grandfather paradox is the Novikov self-consistency principle, which states that if time travel is possible, then only events that are self-consistent can occur. In other words, you can travel back in time, but you can't change the past in a way that creates a paradox. Another intriguing concept is the block universe theory, which posits that the past, present, and future all exist simultaneously. Imagine a loaf of bread with each slice representing a moment in time. The entire loaf exists at once, even though we only experience one slice at a time. If the block universe theory is correct, then the past is not gone, and the future is not unwritten. They both exist, just like different parts of the loaf of bread. This would mean that time travel wouldn't be about changing the past or the future, but about accessing different points in space-time. Chapter 5. Many Worlds, Many Possibilities, the Multiverse and Beyond. Let's explore the mind-blowing concept of the multiverse, a theoretical framework that suggests our universe is just one of many. Imagine an infinite number of universes, each with its own unique set of physical laws and initial conditions. Some universes might be very similar to ours, while others could be radically different. The multiverse hypothesis offers a fascinating solution to the paradoxes of time travel. Imagine traveling back in time and changing the past. Instead of altering your own timeline, you might be creating a new, divergent timeline, branching off from the original. Think of it like choosing a different path at a fork in the road. Both paths exist, but you can only experience one at a time. Similarly, in the multiverse, all possible timelines might exist, and time travel might be like hopping between these parallel universes. While the multiverse remains a highly speculative idea, it has captured the imagination of physicists and science fiction enthusiasts alike. It offers a tantalizing glimpse into the possibility of infinite realities where anything is possible. The future of time travel. Thanks for watching. If you enjoyed this video, don't forget to like, subscribe, and hit the bell icon for more fascinating content. Let us know in the comments what you think about the possibility of time travel. From Einstein's revolutionary theories to the mind-bending world of quantum mechanics, we've explored some of the most intriguing concepts in modern physics. While time travel remains a theoretical possibility, the very act of contemplating it pushes the boundaries of our understanding of the universe and our place within it. Who knows what the future holds? Perhaps one day, time travel will be as commonplace as hopping on a plane. Until then, we can continue to explore the cosmos with our minds, unraveling the mysteries of time and space and marveling at the wonders of the universe.